Hello, beautiful souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. Light is described by scientists as electromagnetic radiation, which means it is a form of energy that moves through space and can interact with matter in observable ways. When researchers study light in laboratories, they measure its properties using instruments that detect wavelengths, frequencies, and intensities. These measurements remain consistent across many experiments, which allows scientists to describe light using mathematical equations and physical models. The word light, in everyday language, usually refers to the visible portion of electromagnetic radiation, which is the small range of wavelengths that human eyes can detect. However, in physics, the term electromagnetic radiation includes not only visible light, but also infrared, ultraviolet, radio waves, microwaves, X-rays, and gamma rays. All of these forms of radiation share the same fundamental nature, differing only in their wavelengths and frequencies. The has an exact value in the International System of Units. The reason light has a finite speed, rather than traveling instantaneously, relates to the structure of space and the fundamental properties of electromagnetic fields, which are described by Maxwell's equations. These equations show that changing electric fields create magnetic fields, and changing magnetic fields create electric fields, and this interplay propagates through space at a specific rate determined by physical constants. The wave-like behavior of light becomes apparent when observing phenomena such as diffraction and interference. Diffraction occurs when light passes through narrow openings or around edges, causing the light to spread out rather than continuing in perfectly straight lines. This spreading is subtle when the opening is large compared to the wavelength of the light, but becomes more pronounced when the opening is similar in size to the wavelength. Interference happens when two or more light waves overlap in space and their amplitudes combine according to the principle of superposition, where the waves align, meaning their peaks and troughs match. The combined amplitude increases, creating brighter regions where the waves are out of alignment with the peak of one wave coinciding with the trough of another. The amplitudes cancel, creating darker regions. These interference patterns have been observed in many experiments, such as the double-slit experiment, where light passing through two closely spaced slits creates alternating bright and dark bands on a screen. The spacing and positions of these bands can be calculated using the wavelength of the light and the geometry of the setup, and experimental results consistently match theoretical predictions. The particle-like behavior of light is observed in different types of experiments, particularly by the equation E equals h times F, where E is the energy, F is the frequency, and h is Planck's constant, a very small number that appears throughout quantum mechanics. The photoelectric effect is a phenomenon that demonstrates the particle nature of light. In this effect, light shining on certain metal surfaces causes electrons to be ejected from the metal. What researchers found through careful measurement is that the number of ejected electrons depends on the intensity of the light, but the energy of each ejected electron depends only on the frequency of the light. This observation could not be explained if light were purely a continuous wave, but makes sense if light delivers energy in discrete packets. The threshold frequency below which no electrons are ejected, regardless of intensity, indicates that each photon must carry a minimum amount of energy to liberate an electron from the metal. Light does not require a medium to travel through. In the 19th century, scientists hypothesized the existence of a substance called the luminiferous ether, which they believed filled all of space and served as the medium for light waves, similar to how sound waves require air or water. However, experiments designed to detect the motion of Earth through this ether, most notably the Michelson-Morley experiment, found no evidence of its existence. The results showed that the speed of light was the same in all directions, regardless of Earth's motion through space. These findings contributed to the development of special relativity, which describes space and time as interconnected. light travels at different speeds in different materials. If light enters a material where it travels more slowly, and if it enters at an angle rather than perpendicular to the surface, one side of the wavefront slows down before the other side, causing the overall direction to change. The amount of bending can be calculated using Snell's law, which relates the angles of the incoming and outgoing light rays to the refractive indices of the two materials. Refraction explains why objects appear bent or displaced when viewed through water or glass. A straight stick, partially submerged in water, appears to have a kink at the surface because light from the underwater portion refracts as it exits the water and enters the air, changing direction before reaching an observer's eye. Lenses use refraction to focus or spread light. A convex lens, which is thicker in the middle than at the edges, refracts light rays inward, causing them to converge at a focal point. A concave lens, thicker at the edges than in the middle, refracts light outward, causing the rays to diverge. Reflection occurs when light encounters a surface and bounces back rather than passing through. The law of reflection states that the angle at which light strikes a surface, measured from a line perpendicular to the surface, equals the angle at which it reflects away. This relationship holds for smooth surfaces like mirrors. When a surface is rough, at the scale of the wavelength of light, each small section of the surface reflects light according to the same law. But because the surface is oriented in many different directions, the reflected light scatters in many directions. This is called diffuse reflection, and it is why most objects around us are visible, even though they are not mirrors. The light from a source, such as the sun or a lamp, strikes these objects and scatters in all directions, some of which reaches our eyes. Mirrors taken in by a material and converted into other forms of energy, often heat. When light strikes an object, some wavelengths may be reflected, some may be transmitted through the object, if it is transparent or translucent, and some may be absorbed. The specific wavelengths that are absorbed depend on the materials, atomic and molecular structure. Atoms and molecules have specific energy levels that electrons can occupy. When a photon with energy matching the difference between two energy levels strikes an atom or molecule, the photon can be absorbed and an electron moves to a higher energy level. If no energy levels match, the photon's energy absorption is less likely, and the photon may pass through or reflect. This selective absorption is why objects have color. A red apple absorbs most wavelengths of visible light, except for red wavelengths, which are reflected. Our eyes detect the reflected red light, and we perceive the apple is red. A material that appears black absorbs most wavelengths across the visible spectrum, while a white material reflects most wavelengths. Transparent materials, such as clear glass, allow most visible wavelengths to pass through with minimal absorption, though some materials absorb specific wavelengths outside the visible range. Energy is carried by light in the form of oscillating electric and magnetic fields. These fields are perpendicular to each other and to the direction of travel. As the fields oscillate, they transport energy from one location to another without requiring the physical transport of matter. The amount of energy carried by light depends on its frequency and its intensity. Intensity refers to the amount of energy passing through a given area per unit time, and is related to the amplitude of the electromagnetic wave. A brighter light has greater intensity than a dimmer light of the same color. When light spreads out from a point source, such as a light bulb, the energy is distributed over an increasingly large area. As the distance from the source increases, the intensity decreases with the square of the distance, a relationship known as the inverse square law. If the distance from a light source doubles, the intensity at that distance becomes has the same amount of energy, is spread over 4 times the area. This principle applies to many types of radiation and is observed in everyday situations, such as how a flashlight appears dimmer as you move farther away from it. Different colors of light correspond to different wavelengths and frequencies of electromagnetic radiation. Wavelength is the distance between successive peaks of a wave, and frequency is the number of wave peaks that pass a given point per unit time. The wavelength and frequency are inversely related through the speed of light, expressed by the equation c equals lambda times f, where c is the speed of light, lambda is the wavelength, and f is the frequency. Visible light ranges in wavelength from approximately 400 nanometers for violet light to approximately 700 nanometers for red light. A nanometer is 1/billionth of a meter, which gives a sense of the extremely small scale of these wavelengths. Within this range, different wavelengths are perceived by the human eye as different colors. Violet and blue light have shorter wavelengths and higher frequencies, while red and orange light have longer wavelengths and lower frequencies. Green and yellow light fall in the middle of the visible spectrum. The colors blend smoothly from one to another, forming the continuous spectrum seen in a rainbow, or when white light is dispersed by a prism. The electromagnetic spectrum extends far beyond the visible range. Radio waves have wavelengths ranging from millimeters to kilometers and are used for communication technologies such as radio, television, and wireless networks. Microwaves have wavelengths from about 1 millimeter to 1 meter and are used in microwave ovens and certain communication systems. Infrared radiation has wavelengths longer than visible red light, but shorter than microwaves, typically ranging from 700 nanometers to 1 millimeter. Warm objects emit infrared radiation, which is why thermal cameras can detect heat. Ultraviolet radiation has wavelengths shorter than visible violet light, ranging from about 10 nanometers to speed of light in vacuum and differ only in wavelength and frequency. Human eyes detect light using specialized cells in the retina called photoreceptors. There are two main types, rods and cones. Rods are more sensitive to low light levels and do not distinguish colors, while cones are responsible for color vision and function best in brighter light. There are three types of cones, each sensitive to a different range of wavelengths, corresponding roughly to red, green, and blue light. The brain processes signals from these cones to create the perception of color. The human eye can detect only a narrow band of the electromagnetic spectrum because the photoreceptor cells respond only to wavelengths between approximately 400 and 700 nanometers. Other animals have different ranges of sensitivity. Some insects can see ultraviolet light, which allows them to perceive patterns on flowers that are invisible to humans. Certain snakes can detect infrared radiation, which helps them locate warm-blooded prey in darkness. The limitation of human vision to a small portion of the spectrum is a result of evolutionary processes and the specific chemical properties of the molecules in our photoreceptor cells. Light spreads gradually from sources. A point source emits light in all directions equally, and the light expands outward in spherical wave fronts. The wave front is a surface of constant phase in the wave, representing all points where the wave is at the same stage of oscillation at a given instant. As the wave front expands, each point on the wave front can be considered a source of secondary wavelets, a principle known as Huygens principle. These secondary wavelets combine to form the next wave front, explaining how light propagates through space and around obstacles. An extended source, such as a fluorescent light panel, can be thought of as a collection of many point sources. The light from all these points overlaps, creating a more complex pattern of illumination. The intensity of light from an extended source does not decrease as sharply with distance as it does from a point source, because the geometry is different. However, at large distances, most passes, and the inverse square law becomes applicable. Shadows form when an object blocks light from a source. If the light source is a point, the shadow has a sharp edge called the umbra, where no direct light reaches. If the source is extended, such as the sun, there is also a region called the penumbra, where the object blocks light from part of the source, but not all of it. In the penumbra, partial shadowing occurs, creating a gradual transition from full shadow to full light. The size and shape of a shadow depend on the size and position of the object, the size and position of the light source, and the distance to the surface where the shadow is cast. Shadows are predictable based on the straight line propagation of light. Geometric optics, which treats light as rays traveling in straight lines, can accurately calculate shadow positions and shapes. Eclipses are large-scale examples of shadows. A solar eclipse occurs when the moon passes between the sun and earth, casting a shadow on Earth's surface. A lunar eclipse occurs when Earth passes between the sun and the moon, casting Earth's shadow on the moon. Mirrors and lenses shape light paths through reflection and refraction. A flat mirror creates an image that appears to be the same distance behind the mirror as the object is in front of it. The image is laterally inverted, meaning left and right are swapped. Curved mirrors, such as concave and convex mirrors, create different types of images. A concave mirror curves inward and can focus light, producing either magnified images when the object is close, or inverted images when the object is farther away. A convex mirror curves outward and always produces smaller, upright virtual images, which is useful for wide-angle viewing, such as in security mirrors or car side mirrors. Lenses bend light through refraction. A converging lens, also called a convex lens, brings parallel light rays to a focal point. Diverging lenses, or concave lenses, spread parallel light rays outward. Combinations of lenses are used in optical instruments, such as microscopes, telescopes, cameras, and eyeglasses. constructive interference occurs, creating bright bands where the path difference is a half number of wavelengths plus a whole number. Destructive interference occurs, creating dark bands. The resulting pattern of alternating bright and dark bands is called an interference pattern. This pattern is evidence of the wave nature of light. Interference also occurs in thin films, such as soap bubbles or oil slicks on water. Light reflecting from the top and bottom surfaces of the film travels different distances, and depending on the thickness of the film and the wavelength of the light, the reflected waves may interfere constructively or destructively. This creates the colorful patterns seen in such films as different wavelengths interfere constructively at different thicknesses and viewing angles. Simple experiments reveal consistent behavior of light. Passing white light through a prism separates it into a spectrum of colors because different wavelengths refract by different amounts. Measuring the angles and using Snell's law, the refractive index of the prism material for each wavelength can be calculated. Shining light on a photocell generates an electric current, and measuring this current under different conditions shows that intensity affects the number of ejected electrons, while frequency affects their energy. Observing shadows confirms that light travels in straight lines. Measuring the time for light to travel known distances confirms its finite speed. Using mirrors and lenses to create images confirms the laws of reflection and refraction. These experiments, repeated many times under controlled conditions, yield the same results, demonstrating that the behavior of light follows regular, predictable patterns. Brightness depends on the intensity of light reaching an observer or surface, which in turn depends on the power of the source and the distance from it. A light source with greater power emits more energy per unit time, creating greater intensity at any given distance. As light travels outward from a point source, the energy spreads over a larger area, reducing intensity, doubling the distance from a source square law. Additionally, absorption and scattering in the medium through which light travels, such as air, can further reduce intensity. On a clear day, the atmosphere has minimal effect on the intensity of sunlight, but fog, smoke, or clouds scatter and absorb light, reducing brightness. This scattering is wavelength dependent, with shorter wavelengths scattering more than longer wavelengths, which is why the sky appears blue during the day and why sunsets appear red. Blue light from the sun scatters in all directions in the atmosphere, making the sky look blue, while during sunset, sunlight travels through more atmosphere, and the shorter wavelengths are scattered away, leaving the longer red and orange wavelengths. Light loses intensity over space, not only through the geometrical spreading described by the inverse square law, but also through interactions with matter. When light travels through any material, even air, some photons are absorbed by molecules, converting their energy into heat or other forms. Some photons are scattered by particles or density fluctuations in the material, changing their direction over long distances. These processes can significantly reduce intensity in clear optical fibers used for communication, special materials, and manufacturing techniques. Minimize absorption and scattering, allowing light signals to travel many kilometers with minimal loss. In ordinary materials like glass or plastic, absorption and scattering are more significant, which is why thick pieces appear less transparent than thin ones. Photons are used to describe light in physics as discrete packets of electromagnetic energy. The concept emerged from studies of blackbody radiation and the photoelectric effect, phenomena that could not be explained using only classical wave theory. In the blackbody radiation problem, classical predictions failed at short wavelengths, predicting infinite energy output, which did not match observations. Max Planck proposed that energy is emitted and absorbed in discrete amounts proportional to frequency. solve the discrepancy, Albert Einstein extended this idea to explain the photoelectric effect, suggesting that light itself consists of quanta, later called photons. Each photon carries energy proportional to the light's frequency and has properties such as momentum. Despite having no mass, the photon model is particularly useful in describing interactions between light and matter at atomic and molecular scales. In these contexts, treating light as composed of individual photons allows precise predictions of energy transfer and probabilities of different outcomes. Measurement affects observations of light at small scales due to the quantum nature of light and matter. When detecting a photon, the act of detection involves an interaction that changes the state of the system. For instance, a photon detector absorbs the photon, removing it from the system. Before detection, the location or path of the photon may not be precisely defined. Quantum mechanics describes it using a wave function that represents probabilities of different outcomes. Upon measurement, the wave function is said to collapse, and a specific outcome is observed. This does not mean the photon did not exist before measurement. Rather, certain properties did not have definite values until the measurement occurred. The Heisenberg uncertainty principle places fundamental limits on how precisely certain pairs of properties, such as position and momentum, can be simultaneously known. These limits are not due to imperfections in instruments, but are intrinsic to the nature of quantum systems. They reflect the wave-like aspects of particles and the particle-like aspects of waves. Probability appears in descriptions of light behavior because, at the quantum level, individual events cannot always be predicted with certainty. Only the statistical distribution consistently agree with these calculations. The appearance of probability does not imply randomness in the sense of disorder. The probabilities themselves follow strict mathematical laws. Time and change are modeled when studying light using equations that describe how electromagnetic fields evolve. Maxwell's equations relate the electric and magnetic fields at each point in space and time, showing how changes in one field produce changes in the other. Solutions to these equations describe electromagnetic waves propagating through space at the speed of light. In quantum mechanics, the time evolution of a system is governed by the Schrödinger equation, which describes how the wave function changes over time. For photons, a more complete description uses quantum field theory, where the electromagnetic field is quantized and photons are excitations of this field. These mathematical frameworks allow scientists to model how light behaves over time, predict future states based on current conditions, and understand how light interacts with matter. Time appears as a parameter in these equations, and changes occur continuously according to the laws encoded in the mathematics. Mathematical equations describe light instead of direct verbal descriptions, because mathematics provides a precise, unambiguous language for expressing relationships between measurable quantities. Words can be vague or interpreted in different ways, but mathematical symbols and operations have exact meanings. Equations can compactly represent complex relationships that would require lengthy explanations in words. For example, the equation E equals h times F precisely relates photon energy to frequency through a proportionality constant. Maxwell's equations, a set of four partial differential equations, describe how electric and magnetic fields behave throughout space and time in a way that would be extremely difficult to convey accurately using only words. Mathematics also allows predictions to be calculated numerically, enabling comparison with experimental measurements. The success of mathematical models in predicting the behavior of light across diverse situations demonstrates the value of position and momentum is always greater than or equal to a certain small value determined by Planck's constant. This is not because our instruments are imperfect, although that can add additional uncertainty, but because the concepts of precise position and precise momentum are not both well defined for a quantum object. At the same time, light does not behave in a disordered or chaotic way. Rather, it follows probabilistic laws that are highly structured and consistent. Light follows statistical patterns over many observations. When individual photons pass through a double slit, one at a time, each photon lands at a specific location on a detector. Initially, the pattern appears random. However, as more and more photons accumulate, an interference pattern emerges, with regions of higher photon counts and lower photon counts corresponding to constructive and destructive interference. This demonstrates that the probability distribution for where individual photons land follows a wave-like pattern. Similarly, in radioactive decay that emits gamma rays, the exact moment of decay cannot be predicted, but the decay rate, expressed as a half-life, accurately describes the statistical behavior of large numbers of atoms. Light emission from atoms also follows statistical rules. Excited atoms emit photons after random time intervals, but the average behavior matches theoretical predictions. These statistical patterns are reproducible and form the basis for understanding and using light in practical applications. Light creates images in cameras and eyes by focusing light from an object onto a surface where it can be recorded or detected. In a camera, a lens gathers light from different parts of a scene and focuses it onto a sensor or film. Each point on the object emits or reflects light in many directions, and the lens redirects light photoreceptor cells detect the light and convert it into electrical signals sent to the brain. The brain processes these signals to construct the perception of a visual scene. The formation of images relies on the principles of geometrical optics, including refraction by lenses, reflection by mirrors, and the rectilinear propagation of light, adjusting the lens shape or position allows focusing on objects at different distances. The aperture size controls the amount of light entering and also affects the depth of field, which is the range of distances that appear in focus. Light enables vision and perception in ordinary life by entering the eye and providing information about the environment. Objects are visible because they emit or reflect light that reaches the eye. The brain interprets the patterns of light detected by the retina to identify shapes, colors, distances, and movements. Depth perception is aided by having two eyes that receive slightly different views of a scene, a phenomenon called binocular vision. The brain combines these views to estimate distances. Peripheral vision detects motion and provides awareness of surroundings beyond the central focus. The ability to perceive color allows differentiation of objects and details that might otherwise appear similar. Vision is a complex process involving optics, physiology, and neurology, but at its foundation lies the physical behavior of light and its interaction with matter. Technology uses principles of light in everyday devices. Optical fibers transmit data by guiding light through flexible strands of glass or plastic, using total internal reflection. Light entering the fiber at a suitable angle reflects repeatedly off the inner surface rather than escaping, allowing signals to travel long distances with minimal loss. Fiber optic communication carries vast amounts of data at high speeds and forms the backbone of modern internet infrastructure. Lasers produce coherent light, meaning the light waves are in phase and travel in a well-defined direction. This is achieved electrical energy using the photovoltaic effect, where photons striking a semiconductor material excite electrons, creating a current. Cameras, projectors, and display screens all manipulate light to create or display images. Lasers behave differently from normal light sources because they produce light that is coherent, monochromatic, and directional. Coherence means the light waves maintain a constant phase relationship, allowing them to interfere consistently. Monochromatic means the light consists of a very narrow range of wavelengths, often perceived as a pure color. Directional means the light is concentrated into a narrow beam rather than spreading in all directions. These properties make lasers useful for precise applications. The process of generating laser light involves placing atoms or molecules in an excited state and using stimulated emission to produce photons. Stimulated emission occurs when an excited atom is triggered by a photon to emit another photon of the same wavelength and phase. Mirrors at both ends of the laser cavity reflect the light back and forth, amplifying it through repeated stimulated emissions. One mirror is partially transparent, allowing some light to escape as the laser beam. Different materials and designs produce lasers operating at different wavelengths, from ultraviolet to infrared. Light remains consistent across different environments in the sense that the fundamental laws governing its behavior do not change. The speed of light in vacuum is a constant. The relationships between wavelength, frequency, and energy hold diverse contexts. Experiments conducted in different laboratories or at different times yield consistent results. When conditions are controlled, this confirms the reliability and universality of the principles. Scientific models of light improve over time as new observations and experiments provide more information, and as theoretical frameworks develop. Early models treated light as rays, which worked well for understanding reflection, refraction, and image formation, but could not explain interference and diffraction. The wave model addressed these phenomena, successfully explaining patterns observed in experiments with slits and thin films. However, the wave model could not account for the photoelectric effect and blackbody radiation. The photon model, introduced by quantum mechanics, explained these phenomena by treating light as discrete particles. Later, quantum electrodynamics combined the wave and particle aspects into a more complete theory, describing light as excitations of the electromagnetic field. Each model remains useful within its domain of applicability. Ray optics works for designing lenses and mirrors. Wave optics is essential for understanding interference and diffraction. Quantum mechanics is needed for interactions between light and matter at small scales. Scientific progress involves refining models, expanding their scope, and recognizing their limitations. Clear definitions reduce confusion in optics and other areas of physics by ensuring that terms have specific, agreed upon meanings. For example, defining wavelength as the distance between successive peaks of a wave eliminates ambiguity. Defining refraction as the change in direction of light due to a change in speed when moving between media clarifies what the term refers to. Technical terms such as coherence, polarization, dispersion, and luminosity each have precise definitions that allow scientists to communicate effectively. When new phenomena are discovered or new concepts introduced, definitions frequency of the speed of light. General relativity extends these ideas to include gravity and describes how light behaves in strong gravitational fields. The consistency of physical laws allows scientists to build on previous work, confident that established principles will not be invalidated by new discoveries, but rather extended or refined. Tests of consistency involve checking that different methods of calculating the same quantity give the same result, and that predictions based on different theories agree where their domains overlap. Unexpected results still follow predictable rules. When an experiment yields a surprising outcome, the surprise usually indicates incomplete understanding rather than a failure of physical laws. Investigating unexpected results often leads to new discoveries and deeper understanding. For instance, the observation that the speed of light did not depend on the observer's motion was unexpected based on prior assumptions, but it led to the development of special relativity, which explained this result through a revised understanding of space and time. The ultraviolet catastrophe, where classical predictions of blackbody radiation diverged from observations at short wavelengths, was unexpected, but it led to quantum mechanics. In each case, careful examination revealed that the unexpected results followed from more fundamental principles that were not previously recognized. Science progresses by confronting and explaining such surprises, integrating them into an expanding framework of knowledge. Repeated experiments strengthen scientific understanding by confirming that results are reproducible and not due to chance or uncontrolled variables. Reproducibility is a cornerstone of the scientific method. If an experiment produces a certain result once, performing it again under the same conditions should yield the same result. Variations in results across trials provide information about measurement uncertainty and natural variability. When many experiments conducted by different researchers in different locations all produce consistent results, confidence in the underlying principles increases. For light, countless experiments measured its speed, confirmed the laws of reflection and refraction, observed interference and diffraction, and validated quantum predictions. The accumulation of consistent results across diverse experiments provides strong evidence that the models and theories describing light are accurate representations of reality. Reasoning about light stays balanced between data and mathematics by using each to inform and constrain the other. Experimental data provide the empirical foundation, showing what actually happens in controlled situations. Mathematics provides the language for formulating theories and making predictions. A successful theory must agree with existing data and make testable predictions for new situations. When predictions match observations, confidence in the theory grows. When they do not, the theory may need revision. This interplay between theory and experiment drives scientific progress. Data without theory can accumulate without providing understanding, while theory without data risks becoming disconnected from reality. By maintaining a balance, scientists ensure that their models are both empirically grounded and theoretically coherent. Understanding improves as scientific language becomes more precise. Vague or ambiguous terms can lead to miscommunication and confusion. By defining terms carefully and using consistent terminology, scientists create a shared vocabulary that facilitates collaboration and comparison of results. Mathematics plays a key role here, as mathematical statements are inherently precise. Symbols represent specific quantities. Operations have exact meanings, and logical relationships are clearly defined. As scientific understanding deepens, language often becomes more technical, introducing new terms to describe newly discovered phenomena or refined concepts. While this can make science less accessible to non-specialists, it allows experts to communicate complex ideas efficiently and accurately. Educational efforts aim replacing them entirely. For example, quantum mechanics includes classical mechanics as a limiting case for large-scale systems. This stability allows scientists to build on previous work with confidence and allows technological applications developed based on established principles to function reliably. The structured frameworks for understanding light, developed and refined over generations, provide a solid foundation for both ongoing research and practical use. Light propagates outward from any source in a manner that can be understood through the concept of wave fronts, expanding through space at a constant rate. When considering a single point source in an otherwise empty region, the light spreads uniformly in all directions, forming spherical surfaces where the electromagnetic oscillations have the same phase. These expanding spheres represent the wavefront. The distance between successive wavefronts corresponds to one wavelength of the light. The energy carried by the light is distributed across the entire expanding surface, which explains the decrease in intensity as distance increases. The mathematical description of this expansion involves the radial distance from the source and the solid angle subtended by any given region of space, allowing precise calculation of how much energy passes through any area at any distance from the source. When multiple sources emit light simultaneously, the waves from each source overlap in space. The principle of superposition determines the resulting electromagnetic field at any point. The electric and magnetic field vectors add together according to their directions and magnitudes, creating patterns of constructive and destructive interference wherever the sources have a consistent phase relationship. This is why carefully arranged arrays of light sources, such as antenna arrays or multiple slits in an interference experiment, can create complex spatial patterns of bright and dark regions. The mathematics describing these patterns involves calculating the path length from each source to each point in space, determining the relative phase of each contribution and summing the contributions while accounting for their vector nature. The result frequencies, so the light passes through with minimal absorption. The slight slowing of light in transparent materials results from the electromagnetic field of the light wave, inducing oscillations in the electrons of the material. These induced oscillations re-radiate electromagnetic waves that interfere with the original wave, effectively reducing the overall propagation speed through the material. Dispersion is the phenomenon where different wavelengths of light travel at different speeds through a material. This occurs because the refractive index depends on wavelength. This wavelength dependence arises from the detailed interaction between light and the electrons in the material. The resonant frequencies of electron oscillations play a key role when white light, which contains many wavelengths, passes through a dispersive material such as glass. The different wavelengths refract by different amounts, separating spatially. A prism demonstrates this effect by spreading white light into a spectrum of colors. Dispersion also occurs in water droplets in the atmosphere, creating rainbows when sunlight enters, refracts, reflects internally, and exits the droplets, with each wavelength emerging at a slightly different angle. The precise angle depends on the wavelength and the geometry of the droplet. Calculations based on Snell's law and the geometry of spheres accurately predict the angular positions of different colors in a rainbow. Polarization describes the orientation of the electric field vector in an electromagnetic wave. Light can be unpolarized, meaning the electric field vector oscillates in random directions, perpendicular to the direction of propagation, or light can be polarized, meaning the electric field oscillates in a specific direction. Linear polarization occurs when the electric field oscillates along a single line. Circular polarization occurs when the electric field vector rotates while maintaining constant magnitude. Elliptical polarization is a more general case where the electric field vector traces an ellipse. Certain materials and processes preferentially transmit or reflect light with specific polarizations. Polarizing filters allow light diffraction grating. It reflects or transmits light from adjacent grooves, interferes for certain angles. The path difference between light from adjacent grooves equals a whole number of wavelengths, producing constructive interference. Different wavelengths satisfy this condition at different angles, so the grating separates them spatially. The spacing between grooves and the wavelength of light determine the angles at which bright spots appear, following a mathematical relationship derived from the geometry and the condition for constructive interference. Diffraction gratings with thousands of grooves per centimeter can achieve very fine separation of wavelengths and are used in instruments called spectrometers to analyze the composition of light from sources such as stars or chemical samples. The pattern of wavelengths present in light from a source provides information about the physical processes producing the light and the materials involved. Coherence length is a measure of the distance over which light maintains a consistent phase relationship. It depends on the spectral purity of the light source. A perfectly monochromatic source emitting a single wavelength would have infinite coherence length, but real sources always emit a range of wavelengths. Even if narrow, the coherence length is inversely related to the range of wavelengths emitted. So a laser with a very narrow emission spectrum has a long coherence length, while white light, containing a broad range of wavelengths, has a very short coherence length. Interference effects are observable only when the path difference between interfering waves is smaller than the coherence length. This is why lasers are used in experiments requiring interference over significant distances, such as interferometric measurements, while ordinary light sources require careful arrangement to observe interference patterns at all. And now, as the light in its quiet journey continues through space, through materials, through lenses and fibers, through clouds, water, and air, there is nowhere it needs to hurry, nowhere it needs exists. Just propagation. Just interaction. Just energy moving as it must. In this ongoing flow, photons travel. Coherence maintained. Interference patterns forming, dissolving. Absorption, scattering, and reflection. All occurring without drama, without urgency. Just as they always have. Just as they always will. And as light follows its path. Through instruments, through eyes, through sensors, through fibers. You may follow your own path, slowing, settling, allowing systems to rest, neural activity reducing, muscles releasing, thoughts thinning, without effort, without demand. Your perception of color, of intensity, of reflection fades naturally as attention itself quiets, like photons dispersing, like energy traveling steadily. You may drift along the same principles, allowing observation and calculation and reasoning to pause as the body and mind pause. Light continues its work silently, even when unseen, even when unmeasured, just as the universe continues, without urgency, without expectation, without concern. And so, as photons travel, as waves and particles, as energy and information, you may remain steady, unaltered, at rest, moving slowly towards sleep, not as an ending, not as a conclusion, not as a final observation, just a quiet continuation within an ongoing system, just as light continues, without effort, without purpose, without notice, and as the natural laws remain